Well, hello everybody, and good morning, good afternoon, or good evening, wherever you may be around the world. We've got quite an attendance here today. My name is Mike Thompson. I'm Director of Engineering at the OpenHW Foundation, and today I'm very pleased to be joined by members of the OpenHW Foundation from CircuitSutra and RISC Design Automation. We're going to be doing a webinar centered on virtual prototyping, high-level synthesis, and advanced DV flows for RISC-V based SoCs. We've got quite a number of attendees today, and that's great. What I'd like to do is just let everybody know about a promotion we're offering. If you stay until the end of the webinar, there's going to be a raffle for attending the Open Community Experience. This is the Eclipse Foundation's premier open source event of the year. And for those of you that don't win, there'll also be a discount code, so you can get a discount on your registration. So please stick around for that. All right, next slide, please. Just a wee bit about the Eclipse and OpenHW Foundation. If you've been involved in open source development for software development for sometime in the last 20 years, you've probably heard of Eclipse. They've been around at least that long. If you've heard of the Eclipse IDE, that's the thing that started it all. That was 20 years ago, and now there's 400 projects within the Eclipse ecosystem. The OpenHW Foundation is pleased to be part of that. We're the new kids on the block. We're the open source hardware arm of Eclipse. Today, we're going to be talking about a specific project within the OpenHW Foundation. This is the Core 5 MCU project. This is an Eclipse project that curates a complete microcontroller platform that targets low-power edge IoT applications. The heart of this MCU is the CV32E40P. This is a four-stage RISC-V processor core that optionally supports floating point, optionally supports SIMD operations. This thing is specifically targeted for low-power edge IoT applications, which makes it a perfect processor core for the MCU. So I used the word ecosystem earlier, and I really do want to emphasize that there is an ecosystem around here. There's a graphic there of the block diagram of the Core 5 MCU. Everything you see here is available as open source RTL, including the test benches, including synthesis scripts, all the rest of it. It's on GitHub right now for you to use. Another click. We treat documentation just as seriously as we treat our RTL. So the MCU has a complete user manual. The team at CircuitSutra has made monstrous contributions to this. We're very grateful to that team for that. The user manual is also available on GitHub as an open source artifact. An MCU is not much use without some sort of software development environment. So of course we have one of those, also open sourced. And if that screen that looks on your monitor looks a little bit familiar, if it looks a little bit like the Eclipse IDE, that's because it is. So our software development environment is based on the very popular Eclipse IDE. If you're looking to develop hardware implementations, there's a couple of ways that you can go. On your right-hand side is a clamshell that we built for a third-party commercial development platform for Xilinx FPGAs from Digilent. We've got all the open source IP required to build a bitmap for this, and now you can run the MCU on an FPGA. You want to go with a custom ASIC, you can do that. We've got on the left-hand side, you'll see that there is a PCB dev kit. That thing comes with all the schematics, all the symbols, all the screens, the bill of materials. Those are all open source artifacts available on GitHub. And the next one, there is a UVM environment for this, and there's also this image here, this picture. This is my very favorite implementation of the Core 5 MCU. This was done by a team at the University of Saskatchewan. The ASIC you see in the middle is a rad-hardened device for space-based applications. And if the board that it sits on looks familiar, it's because the team at the University of Saskatchewan was able to leverage the dev kit, all the schematics, all the screens, and all the symbols, all the rest of it, because they're all open source artifacts. Everything I talked about just now, it's all on GitHub. The MCU, the dev kit, the UVM environment, the SDK, some examples, the dev kit, the CLI tests. These are all open source artifacts, all on GitHub right now. All right, well, that's it for me. But wait, there's more. It's just like the commercial. This MCU environment is very, very cool, but it's not really worth anything unless you can develop software for it, unless you can extend it to do your own designs. Maybe you want to do your own peripherals. So our colleague Umesh Sisoda from CircuitSutra is going to introduce some of those technologies. So with that, I will hand it over to Umesh.
Thanks, Mike. Hi, I'm Umesh Sisodia, founder and CEO of CircuitSutra Technologies, and I will be providing a brief overview about CircuitSutra. At CircuitSutra, our primary focus is higher abstraction shift left methodologies. We develop the fast simulation models of CPU, IP, SoC, and system at an abstraction level above RTL using high level languages like C++, System C. These models enables several design and verification steps which are not feasible in the traditional RTL to GDS flow and allows to shift various crucial steps and decision making to the left, thus reducing the overall cost and time to market for a new chip. These methodologies significantly enhance the probability of success for a semiconductor chip or electronic systems. We provide the modeling services for the modeling of CPU and SoC. And as part of this, we set up the world-class team of modeling experts to work as the extension of customers' team, either remotely from Circuit Sutra's office in India, supporting the customers across the globe, or on-site on the customer premises in India or US. Our team comes with a strong foundation skills which are required for the modeling projects and can easily adapt to the customer specific tools or modeling methodologies. In a typical customer engagement, we generally work with a central methodology team and at the same time support various BUs and various groups for the effective deployment of those methodologies. And in some cases, we even support the customer's customer for the effective deployment of these methodologies. We have a highly specialized training system C for virtual prototyping, which we conduct for select few customers. We also provide reusable modeling methodology that helps customer to get started quickly with their modeling activities. This can be useful for the companies who are new to modeling and are just getting started. We also do some joint R&D project where we partner with the customers to develop the innovative modeling IP and methodology. In such projects, we share the cost and the intellectual property is co-owned. Recently, we started a joint project with Simplest Micro for the performance modeling of RISC-V CPU. At Circuit Sutra, our mission is to accelerate the adoption of higher abstraction shift left methodologies in the industry, and we support all the stakeholders of the industry, including the CPU companies, SoC companies, IP companies, or the algorithmic companies. We are in the business for more than 20 years now, and perhaps we are the only company which is 100% focused on and have in-depth understanding of these higher abstraction methodologies. And most of our customer engagements are active for more than 10 years, and we are their de facto modeling partner. In this journey, we received several awards, including a recognition by Accelera for driving the standards in the Indian ecosystem. As we all know, RISC-V is an emerging and open source CPU architecture, and it is rightly positioned to fuel the innovation in the semiconductor industry across various application areas. At CircuitSutra, we developed a reusable modeling framework for the RISC-V ecosystem. We have CST-ISS, a CPU modeling framework that enables you to use any open source ISS in System C or any other simulation framework, or develop your own custom ISS very quickly. We are currently extending this framework for the performance modeling as well. We have a reference virtual platform of Corvi MCU developed using CircuitSutra modeling methodology, which is based on standard System C TLM 2.0. It's mainly suitable for embedded software development and testing, and further extended for advanced flows that will be covered in the webinar today. This can be useful for the companies involved in the development of RISC-V CPU, RISC-V based SoC, or the IP for the RISC-V based SoC. It enables them to effectively and quickly deploy higher abstraction shift left methodologies. We will be adding more components to this framework based on the customer's requirement. That's all I wanted to cover today. Thanks for attending. Now I'll hand it over to Ellie Burns for the next session.
Hi, thanks, Mish. I'm Ellie Burns, Head of Marketing with Rise Design Automation, and I want to give you just a brief overview of Rise and what we're doing and what we're all about. So I'll start with kind of our purpose, which is really to enable a shift left of the SoC design process and deliver implementable, verified, high-quality RTL, just much faster in a way that it's practical and exists today. Who we are, we're a veteran EDA team that with decades of experience. Rise was founded in late 2022. We officially launched in 2024, so came out of stealth in 2024, and currently about 10 employees, all located here in the US. So when I say the industry must shift left, what we're seeing is we need massive amounts of productivity, 100x, 1000x, in order to be able to do these kind of next generation chips over the next decade. And I don't mean, it's not really enough to just say, okay, I'm going to make the verification more productive, or just the design, or just software. You really need to uniformly shift left the entire design process and bring all those things with you. So cut your design and verification times, massively without increasing your staff. Early software development, you cannot wait for all of the hardware software interactions before have to validate before RTL is complete. Early system validation. Now we've got all of these massive pieces of IP, and you find critical bugs between the interaction with them and with the software very late in the process. So you need to shift that left very early. Agile requirements, the specs are changing constantly, especially now with some of these new AI chips. So you need to be able to react quickly to that, be able to have different versions of your IP, be very agile in your requirements. Architectural exploration, again, you don't want to do just one architecture, you want to find the best one for power and performance. And then, of course, AI everywhere in the chip design process. How can you apply AI with today's models, with today's infrastructure? How can you get the most use out of that for your productivity? So that's what I really mean by shift left the entire design process. And essentially what Rise is doing is we really bridge this gap between architecture and silicon and in design. And we do that kind of with three major columns that we'll be talking about. looking at it from intent to implementation, so from specification to algorithm to system model through RTL. We bring up all of that into the system level validation. So you don't want to have your hardware separate from your system validation or wait too long. So we be able to do that with hardware software integration at the system level, which we're talking a lot about today. And again, powered by next generation high level synthesis, which is essentially the platform that enables us to be both predictable and scalable. Okay. So that's just a real brief introduction. I'll come back and talk about some more later when we get into deeper dive into the product. But that's all for now. And up next is Ayush Miyawati. I'll turn it over to him. Thank you.
Hi everyone, I'm Ashmi Vati, a member of consulting staff at CircuitSutra Technologies. Today we are diving into an advanced design and verification flow for RISC-V based SoCs. We'll be focusing on the intersection of virtual prototyping and high-level synthesis, looking at how CST-ISS accelerates the development of the VP of Open Hardware Group's core VMCU. So we'll have a quick overview of core VMCU, development of its virtual prototype using CST-ML and CST-ISS, overview of and supported features for CST-ISS, success story and benefits, and CST-ISS feature roadmap. The core VMCU is an open source RISC-V microcontroller platform from the OpenHW Foundation. It uses the CV32E40P as a core. It's a 32-bit IMCA core optimized for embedded efficiency. And we can see the block diagram. It's a feature-rich SoC integrating instruction and data memories, an embedded FPGA, UDMA, advanced timers, and a full suite of peripherals like UART, QSPI, and I2C. It's specifically designed for the low power demands of IoT and edge compute. To support pre-silicon software development, we developed a register-accurate, loosely timed virtual prototype of the core VMCU. We used a CircuitSutra modeling library and our virtual prototype starter package and applied several layers of abstraction. We removed the physical clocks, replaced the pins with TLM 2.0 transactions for memory accesses, and implemented only the functionality that is visible to the software, creating a high performance environment perfect for CI/CD automated firmware testing. At the core of this virtual prototype is our proprietary CPU modeling framework, which is CST-ISS. Critical components of a CPU model are an instruction set simulator, an interface to integrate it with the simulation environment, for example, systemc, and other features like GDB, debug, tracing, etc. CST-ISS acts like a bridge, which integrates any ISS written in C++, which can be RISC-V, ARM, or any other architecture, with the systemc simulation environment and does all the heavy lifting, providing all the other features. The CST-ISS interface here is the actual interface that needs to be implemented in an ISS to make it compatible with the framework. So CST-ISS is the CircuitSutra system CPU wrapper interface. It can be integrated with any simulator, ARM, RISC-V, etc., developed using C, C++. Result after integration is a systemc-based functional CPU model. Application areas include, but are not limited to, virtual prototyping, architecture exploration, firmware development and testing, and it acts as a reference model for RTL verification. So right now, for any RISC-V design implementation idea to go to the virtual prototype full SoC simulation, we have a lot of simulators available, just like Spec, Whisper, and Impact. However, these ISS are not equipped with the native support for an SoC level simulation or advanced higher abstraction methodologies needed for virtual prototyping. CST-ISS helps in bridging this gap, and it also offers more features like GDB, trace, printf from a unified framework. The CST-ISS comes equipped with a lot of features. For example, using any ISS in plug-and-play fashion, so we can develop a custom CPU model quickly by leveraging the reusable features. We can use these multiple simulators as a foolproof verification for our RISC-V design. These common features that are listed down here are independent of the underlying ISS's native compatibility with them. We also support vast variety of RISC-V extensions. We just have to pick the right ISS as per the use case. And currently we have tested 4 simulators, Spike from RISC-V software, V from Chips Alliance, Whisper from Tenstorrent, and Impact RISC-V from Google. We have ability to add more and also custom simulators. For developers, we only need to focus on the simulation. All the other functionalities come from CST ISS. Dynamic selection of ISS means no recompilation required. So individual ISSs have their own pros and cons and can be selected based on the use case. For example, Spike is functional accurate but not high performance. Veer is high performance but limited functionality. Whisper is improved Veer but again decreased performance. And then Impact RISC-V is highly configurable research framework from Google. Using the multi-ISS workflows, we can run the same set of benchmarks on the SoC and compare the performance and pick the right ISS for the use case. For example, the left plot here shows that Veer performs better than Spike for majority of the benchmarks. The right plot shows that with increase in number of tri-stone runs, Spike overtakes the performance graph. So with this, we can infer that for smaller workloads, we should use Veer. For larger ones, we should target Spike. Now let's quickly see our multi-ISS workflow in action. So here we have a common config.json file where we are configuring the ISA to be 32, then ISS lib is impact RISC-V, and this is the command line. We ran the test. Now we'll use the Spike simulator, the same command line. It's again run using that. Now Veer, and now only one line change to run with Whisper. And we don't have to recompile anything. The CST-ISS supports GDB debugging for both software and hardware code, supporting software code debugging environments, opening up opportunities to evaluate the impact of software on the hardware in real time, making optimizations and finalizing the partitioning. This also ensures integration with the standardized tools and tool chains. For example, we will see the breakpointing and other features in the next slide. So we have a software event test running on the Core VMC virtual prototype. Let's quickly see it in action using GDB. So we have a configuration for the launching the virtual prototype. Then we have a configuration to launch the test to attach on GDB TCP port. As we can see, we have two call stacks here, one for firmware, one for hardware. And we have started with the breakpoint in the firmware code. Then we have reached the breakpoint in the hardware code. We can see the plumbing, which reaches from TCDM to APB, and then we can see whether the right IP has been reached by the firmware or not. And this is how we can determine whether the test that we wrote has passed or failed. So beyond GDB, we are fully compliant with the official RISC-V debug specification. This ensures that our virtual environment behaves exactly like a real hardware as described in the RISC-V specs. CST-ISS is compatible with the standard ecosystem tools like OpenOCD and commercial debug probes, allowing external tools to control and investigate the simulation transparently. Now let's quickly see the external debug support in action. We are running the same software event test on a RBB port launched from the CST-ISS, running the OpenOCD to connect on that RBB port, which is remote bitbank. Then running GDB to target OpenOCD's 3333 port. And we can see we are able to hit breakpoints, we are able to set flags in the test, then we are able to run breakpoints, run some next or step commands using GDB, investigate the whole data path here as well, just like a real hardware would do. And we have seen the test is passed. So before looking at the trace support, let's understand what is tracing. So tracing is the language used by the processor to communicate what's happening when a program is executed. This means the instructions that are executed, use of memory cache, occurrences of interrupt exceptions. This gives opportunities for debugging and profiling used in bottleneck analysis. Examples include ARM ETM, Intel Processor Trace, PowerPC Nexus Trace, and RISC-V E-Trace and N-Trace formats. CST-ISS also implements RISC-V N-Trace, which is compliant with the official N-Trace specification. And we can dump the trace data in the trace sink or a file. In addition to this, CST has developed their own decoding utility that connects with the model over TCP port, supports packet generation for debug mode, entry, exit, and interrupts, supports configurable output generation, instruction trace or the decoded messages, and also parses the trace data from a bin file, which is configurable. Let's quickly see the TCP-based trace support in action. So we are running it on a TCP port 1234, and this is the same set software event test. And now we'll run it using ISS. So we can see the model is waiting to be connected, and we are connecting it using the same port, and we have decoded the messages, and the output will be in the trace data.txt file. And we can compare it with the test logs. Let's also see the bin file support for the trace. Now instead of TCP, we will use an offline decoding. So we have generated the bin file. Now we'll launch the CST and trace decoder to parse it from the file. And we can see the trace data.txt now has this. And we can also dump the decoded messages as it is, as the trace has encoded them in their format. So what is semi-hosting? Semi-hosting is a lightweight method to provide host-target interactions. Host can be OS kernel, and target is the firmware running on simulator, which includes console input-output, file input-output, exit codes, and system calls, for example. ISS like Spike support this functionality natively by using HTIF, but this is not supported by all the ISS out of the box. CSTIS provides a non-intrusive method of semi-hosting, which can be utilized by the software running on the underlying ISS. It's a unified method, and it requires no changes in the ISS code. It's a plug-and-play. So printf statements here are explicitly handled by the CST-ISS framework and not the underlying ISS. It's an easy-to-extend interface. That means you can easily add more features down the line, and it's a lightweight mechanism, resulting in performance boost overall. So here we use RISC-V benchmarks, and the left plot shows the comparison between standalone Spike integrated with CST-ISS and with CST-ISS semi-hosting. The right plot clearly shows the difference between integrated Spike with native printf and the CST-ISS semi-hosting. And we can see the green plots are offering a bit more performance here, which is the CST-ISS semi-hosting support. So managing all these features is simplifies to a multi-level configuration system. Where we can configure system C parameters and underlying ISS configurations using the same command line. So here we can see the command line will look like something like this. Binary of the platform is given within first parameter, which is ISA, which goes to the underlying ISS. Then ISS selection, which ISS to pick. The RBB port, which is CST ISS configuration, and the test firmware to run. Now to make it more user-friendly, we also support configuring using a JSON file to collect all the parameters in a single file. And these are both CST ISS plus the underlying ISS configurations. Here we can see this is what the JSON file looks like. And we give the ISA to the underlying ISS slave for the ISS selection, enabling trace, CST ISS parameter, forcing trace to be enabled without writing to the registers, tracing into a file, and then the test output should be stored in the test log. To date, CST-ISS has been successfully deployed for validating the Core vMCU and testing RTOS compatibility for platforms like FreeRTOS and ThreadX. We have been also making use of the RISC-V tools and tool chains, and consuming mainstream tools like compilers, GDB, OBJDump, etc. Looking ahead, our roadmap includes support for multi-core and hypervisor modeling, adding key mode INEMU to the supported ISS list, extending the framework for ARM architecture, adding support for more RISC-V standard tools, and strengthen the verification flows. Now I would like to invite Jayesh Trivedi, my colleague, to take this presentation forward and discuss in more details about the advanced design and verification flows for RISC-V. Thank you.
Thanks, Ayush. Great walkthrough of the Core EMC virtual prototype and the CSTISS. Hi everyone, I'm Jayesh Trivedi, Senior Member Technical Staff at CircuitSutra, and in this presentation, we will cover the following. We will start by looking at how we extend the Core EMC for edge detection, followed by an architecture overview. We then will dive into the use case and data flow, specifically how we implemented the image pipeline using the micro DMA and eFPGA subsystems. We'll see all this running in a demo. In the second half, we'll cover the complete design and verification methodology, moving from executable specs to synthesizable RTL. We will detail the hardware-software co-design cycle using transactional level modeling and high-level synthesis. We will also be covering the performance difference between the loosely timed transaction level model and the high-level synthesis model, and also look at the future scope of work. Now, let's look at how we integrated the edge detector into core VM's SoC. To understand the integration, we first look at the existing micro DMA subsystem. This subsystem already features a dedicated camera module designed to interface directly with external sensors. It manages the entire front-end process, that is, capturing the raw feed, performing initial processing, and efficiently moving image frames into the system memory. This makes the SoC a versatile platform for both static imaging and real-time video applications. The true flexibility of the core VMCU, however, lies in its integrated eFPGA module. This embedded FPGA fabrics allows us to hardware accelerate specific workloads without redesigning the entire chip. To optimize the SoC specifically for image processing, we leverage this fabric to implement the custom edge detector IP, giving us high performance, low latency path for image processing directly on the chip. Moving on to the internal architecture, we focused on maximizing the efficiency of that eFPGA block. The eFPGA has two separate memory regions, one for control and status registers and one for general data storage. The eFPGA also features multiple different interfaces for interrupts, APB bus, clocks, etc. Rather than redesigning these interfaces, we seamlessly integrated the edge detector IP by utilizing them as they were. One of the most critical aspects of this design is the data path. The IP communicates directly with eFPGA's internal memory. This memory is tied into the rest of the SoC via the high bandwidth TCDM interconnect. This is vital because it ensures that the process data is accessible to other system components with minimal latency, maintaining the high throughput required for real-time processing. Now let's look at the edge detection IP itself. At its core, the IP is designed to process a grayscale image stream in real time. It implements the widely recognized Sobel edge detection algorithm, which is deterministic and pipeline friendly. For each pixel, it computes two outputs: the gradient magnitude, which represents the edge strength, and the gradient angle, which gives the edge direction. Sobel algorithm works by convolving a three-tab gradient kernel across the image, one horizontal pass and one vertical pass. The results are combined to get the magnitude and the angle. The use cases, it's a fundamental step for object background separation. By identifying these boundaries, we can isolate specific objects for analysis. Second, It allows the SoC to detect structural features like lines and contours, which are essential for navigational or alignment tasks. Finally, it serves as a critical pre-processing stage. By filtering down the image to its most essential features, we significantly reduce the computational load required for subsequent stages like image segmentation or complex feature extraction. Now let's look at the operational flow of the edge detector IP. The process begins with the configuration phase, where the firmware writes to the control and status registers of the edge detector IP to define the image dimension and memory base addresses. That is, where to read the input grayscale image from and where to write the output data. Once the setup is complete, the firmware writes to the Go CSR, which triggers the IP to begin processing. Upon receiving this trigger, the IP autonomously reads the input image from the memory, performs the edge detection, and writes the process result, that is the magnitude and angle data for each pixel, back to the memory. Once the operation is finished, the IP issues an interrupt to the firmware to signal that the output data is ready. The interrupt-driven handoff is important as it keeps the CPU from busy waiting and ensures that the pipeline stages are properly sequenced without falling. Now, let's put the board level picture together and see the end-to-end data flow within the core VMCU. We have an external camera sensor model connected to the micro DMA camera interface of the core VMCU. The camera model loads the real image files from disk and feeds them into the micro DMA as if they were coming from a physical sensor. On the output side, we have a simple display model connected to the UART interface. It receives the image stream and saves it to a file, which we can then open and inspect visually. The software application running on the virtual platform ties everything together. The process begins at the camera sensor, which streams a raw RGB image to the micro DMA camera module. The micro DMA hardware processes this feed, converts it into grayscale format, and stores it directly into the eFPG memory via the high-speed TCDM interconnect. Once the transfer is complete, the camera module issues an interrupt to the phone. Upon receiving this interrupt, the firmware configures and triggers the edge detection IP. As discussed, the IP autonomously reads the grayscale image from the eFPG memory, performs the processing, and writes the final edge detected image data back to the eFPG memory before issuing its own completion interrupt. In the final stage, the firmware configures the microDMA UART module to fetch this process data and transmit it to an external display. The display then receives the stream, allowing us to visualize or stores the result as an image file. Now, let's look at the edge detection video demo in action. In this demo, we are running the compiled executable of the core VMCU board. We also have the pre-compiled library of our firmware test case and our ISL library. The input source image is a 240 by 240 color image of a house. The input image's directory path is passed to the emulated camera sensor via config parameter. The camera sensor will load all the images present in this directory. The configuration is managed through a config.json file. Shifting to the terminal, we initiate the execution of our core VMCU binary. Note the command line arguments. We are explicitly passing the IESA library alongside our custom edge detection firmware. As soon as the execution begins, the system logs provide a real-time view of the different stages of the image processing pipeline. The micro DMA camera captures the frame and initiates the grayscale conversion. Once that grayscale image is processed and stored in the memory, the first interrupt handler is triggered. The firmware then configures the edge detection IP and triggers the edge detection. The IP then takes over, and within milliseconds, a second interrupt confirms that the edge detection is successfully done. Finally, the logs show that the data is being piped out, transferring both the intermediate grayscale image and the final edge detected image via the UART to our external display module. The display module that we currently have stores the received images as files. The image underscore zero file that you see is the grayscale image, which is the output of the micro DMA camera. The image underscore one is the final processed image. By comparing the original input to the grayscale conversion and the final edge detected image, you can see how efficiently the IP performs feature extraction in real time. Now, let's look at the design and verification flow that we use to develop the edge detector IP, specifically leveraging the TLM model and virtual platforms. This process is broken down into six distinct phases. Phase 1 was establishing the functional specification, what the IP does, what its interface looks like, how it interacts with the SoC memory map. This is the foundation that everything else is built upon. Moving on to phase 2, we developed a loosely timed transactional level model using the CircuitSutra modeling methodology. TLM or transactional level modeling models the IP's behavior at the transactional level, that is, correct data in and correct data out without simulating individual clock cycles. This level of abstraction is ideal for early verification. Alongside the TLM model, we also built a unit testing framework, a set of directed tests that exercise the IP's functionality in isolation. Through the standalone unit test setup, we were able to catch design flaws and refine our specs long before touching the HLS or the RTL. Phase 3 was integrating the TLM-LT model into the core VMC virtual platform. Instead of just running unit tests against the IP in isolation, we now run the actual target software application against it. The same firmware that reads from the camera sensor, triggers the IP, and sends output to the UART display. This is software-driven verification. If the firmware exposed any mismatch between what the spec said and what the software needed, we caught it here. This phase is also where we refine the ISP specifications iteratively. As we run the firmware against the TLM model, we identified areas where the spec needed adjustment. To make the IP more effective for this specific use case, to make it more compatible with core VMC's memory structure, and to make better software hardware partition decisions. For example, deciding which computations belong in the hardware versus firmware, and how the interrupt scheme should work. These are the decisions you want to make at the spec level, not after the RTL is written. With a validated, refined spec in hand, Phase 4 was developing the HLS implementation. The design team took the finalized specification and implemented it in HLS, writing the hardware behavior at a cycle accurate level that the HLS tool then synthesizes into RTL. In parallel, we developed a TLM adapter for the HLS implementation. This adapter wraps the HLS model so that it exposes the same TLM interfaces as our original TLM model. That's a critical design decision because it means that the HLS implementation is a drop-in replacement for the TLM model in any context that uses those interfaces. Phase 5 shows the payoff of that decision. We took the exact same unit testing framework from phase 2, unchanged, and ran it against the HLS implementation through the adapter. Same test inputs, same expected outputs. Any behavioral differences between the HLS model and the golden TLM reference was immediately visible. The adapter is what makes this possible. Without it, you'd need to write a new test framework for the HLS model from scratch. Finally, in phase 6, we perform the ultimate system integration. We returned to the core VMC virtual platform and replaced our original TLM model with HLS implementation and its adapter. Because we reused the same software application for validation, we could confirm that the actual hardware accurate implementation performed exactly as intended within the full SoC environment. This seamless plug-and-play transition significantly reduces our integration risks. To conclude our technical analysis, let's look at the simulation performance numbers because they illustrate something important about how to use these two models. For single iteration, the TLM model completes in 0.39 seconds. The HLS implementation with the TLM wrapper takes 3.59 seconds, roughly 9 times slower. At 100 iterations, the TLM model finishes in 6.15 seconds. The HLS model takes 4 minutes and 29 seconds, roughly 43 times slower. The gap is expected and intentional. The TLM model abstracts away clock cycle. It tells you what the computation produces, not how many cycles it takes. The HLS model simulates the actual hardware behavior cycle by cycle, every pipeline stage, every register transfer. That detail is what you need to verify timing correctness and catch structural issues before synthesis. It costs simulation. So the two models serve different purposes in the flow. We use the TLM model for rapid software iteration and algorithm tuning, and then switch to HLS model to verify timing accuracy and ensure that the design is hardware ready for RTL synthesis. The methodology is designed to use the fastest appropriate model at each stage, allowing us to balance development speed with implementation precision, giving us the best of both worlds. Looking ahead, our future work focuses on closing the gap between the HLS code and the actual hardware. The next step is to take the RTL generated by the HLS tool and integrate it into our verification flow. To do this, we will develop a transactor and adapter set specifically designed for co-simulation, a bridge that lets the synthesizable RTL communicate with the same System C virtual platform environment that we've been using throughout. Most importantly, we will validate the RTL using the same exact software application and test bench. By keeping the software constant while increasing the hardware detail, we can ensure 100% functional parity between our initial concept and the final silicon ready RTL. To wrap up, here's a quick summary of what we have achieved. Firstly, we successfully took the design from functional spec through to a full HLS implementation. Using this flow allowed us to refine the architecture early on. A major benefit was verification reuse. We were able to use the same test bench and firmware test across every phase, which saved a lot of time and kept the testing consistent. The iterative refinement loops between the specs and the virtual platform really helped ensure that the design was robust before we finalized it. The current status is that the edge detector IP's HLS model is fully integrated and verified within the core VMC system. That concludes my presentation. Thank you. I will now hand it over to Mike, who will be presenting the RISC-V Agentic AI Spec to Silicon Design Flow.
Hi, it's Ellie Burns again, Head of Marketing here with Rise Design Automation. In this section, I'll give you a brief introduction, and then we will turn it over to Mike Fingeroff, our Chief of High-Level Synthesis, in order to give us a detailed live product demonstration to give you more clarity about how the product really works to get you from spec into high-quality RTL. So you saw this slide earlier in the introduction. You'll see it again. Again, we're about bridging the gap between architecture and design from intent to implementation and powered by next generation HLS. And so what we'll do is we'll take a little bit deeper dive into all of these three aspects. I want to introduce to you the RISE platform architecture, which is essentially what enables us to go from system intent to both silicon and software in parallel. It is basically starting with system intent and delivering through Agentic AI and the RISE specialized agent an executable specification, which is the hardware description, which then flows into the RISE high-level platform. And that executable specification then also enables into the virtual model and the system level design, enabling this parallel enablement between hardware and software. And essentially, one intent, one description of your system intent, and three different results of that, which is the software ready model, the production quality RTL, and the verification environment. So we'll dive down into each of these pieces individually. Next, I wanted to introduce to you to the RISE agents. This is the power behind the Agentic piece of the system. And really its purpose is to take that high-level system intent, that high-level specification, and turn it into the executable and synthesizable specification that will feed down into the rest of the RISE tool chain and the other tool chains. And really the important part of this is that this is a closed loop tool-gated system where the LLM and the models will do a propose model. And that propose is also not only model agnostic, it can use any frontier language model, but it's grounded in skills-based hardware knowledge and RISE knowledge. And so it knows how to it understands hardware. It understands how to create a quality high-level model. It then uses both the RISE toolchain and various other EDA toolchains to compile, evaluate, synthesize, verify, and this is what gives it its deterministic result, is that the model proposes, the tools evaluate, and then the agents decide. Is the specification met? Are the goals met? Are the target met? What else should we be doing? What else should we be doing next? Again, completely flexible, as I said, can use any type of LLM that you choose, local or in the cloud, but it's this closed loop system that proposes those high level models and uses tool truth to decide what to do. Now I want to talk about the RISE next generation high level platform, which is really the key differentiator and the deterministic engine behind the whole flow from AI generated silicon. It's next generation high level synthesis primarily for two, really, besides all of the AI that we have in here to help you generate, because it is very predictable with strong correlation to production quality RTL synthesis tools, whether you're using a design compiler, Genus, whatever. So within 5 to 10% correlation and 3 to 10 times faster than existing tools. So basically you get this loop from your high level executable specification down into your production quality RTL extremely quick with a strong correlation and knowledge that what high level synthesis is giving you is actually what you're going to get all the way through your RTL synthesis tool. We support System Verilog, System C and C++ to enable both RTL designers and architects to really come together using this tool. And there's clear visibility all the way from the high level executable specification with debug and analysis through every step of that transformation. Built as an open platform where we can extend with other domain languages and other parts of the synthesis, and visibility inside of each of that stages so that you can see exactly what is happening during this transformation. Then it's the executable spec, the high-level model, wrapped in a TLM2 interface that we can do that enables you to shift left the system validation, because it's a hardware realistic model that's been annotated with latency and throughput, but much, much faster. So you can do rapid exploration and early detection of system bottlenecks, not only this hardware and software co-verification. So I just want to do a real quick intro of some of the pieces of verification. Really, one of the cornerstones of the verification inside of the RISE environment is that you can take the same inputs and drive your algorithmic model, your high-level model, and your RTL and compare and validate the results. This is a key aspect of the verification, and that you don't end up with models out of sync or that do not have the same functionality, because we built this into the verification environment. Okay, that's enough for intro. Let's turn it over to Mike Fingeroff for the RISE AI Spec to Design demonstration. So he'll walk you through the tool using the AXI-based edge detector accelerator that you've seen throughout this presentation.
RISE AI enables a direct path from high-level design specifications to synthesizable System C with matchlib code, dramatically reducing the manual effort required to build complex hardware systems. What makes that possible is not just a general-purpose LLM, but a system grounded in RISE-specific agents, reusable skills, and a knowledge base of canonical design examples. These include standard integration patterns, established coding conventions, and reference IP such as the RISE AXI managers, stream converters, and control plane building blocks. With that context, the model can reason about how to assemble real HLS designs in a way that matches RISE's expected architecture and coding style. Instead of handwriting control logic, interface glue, and top-level interconnect, you describe the architecture and interfaces in a spec form, and RISE AI uses that combination of domain knowledge and generation capability to produce a complete connected design. In this example, we'll walk through how a SOBL edge detection pipeline is constructed, from a control specification through top-level integration, all the way to code that can be compiled with RISE HLS to generate RTL, automatically verify correctness, and estimate power, performance, and area. We start with the control specification, which defines the software interfaces, MIMO registers for image size and AXI parameters, along with the go signal that drives execution. From this spec, RISE AI automatically generates a synthesizable System C control block, including the AXI write slave, register storage, configuration wiring, and start signal fan-out to each stage of the pipeline, eliminating the need to manually implement control logic or register maps. Here's the top-level spec. The goal is to integrate existing IP, the control that we generated, the SOBL stages, and AXI read-write masters into a single System C module running at 1 pixel per clock. At the top level, we expose clock, reset, done, and AXI interfaces. The result is a clean top-level integration that stitches together pre-built IP using standard RISE and matchlib interfaces. RISE provides RDA Analyzer, a VS Code extension, to allow designers to perform detailed analysis of the synthesized design. Let's go ahead and walk through the edge top design that we synthesized previously. Edge top contains multiple synthesized modules, and the instance report shows that the magnitude angle is about 90% of the design area, not including memory area. And we'll see why this is in a moment. Zooming into the vertical gradient, this is where the line buffer memories live. The design infers 2 single port RAMs, line buff 0 and line buff 1, each holding a full image row. These are marked with the HLS RDA memory pragma, which causes the arrays to be inferred as memories. Magnitude angle is where the heavy math lives. It computes a square root using the AC math library piecewise linear approximation and an arctangent using the AC math Cordic implementation, which is why this block has 12 pipeline stages as its iteratively rotating vectors over multiple cycles. Despite the complexity, the design is still able to achieve 1 pixel per clock throughput. In the same fashion that we generated the RTL from a spec, the edge top test bench is also generated from a test bench specification along with the generated HLS design. The test bench loads an input image, programs a DUT through the memory mapped I/O, and waits for completion. Afterward, results are read back and compared against a software reference. We then automatically run RTL co-verification using the generated RTL and the same System C test bench. This works because HLS produces verification adapters with transactors that bridge pin-level RTL to high-level transactions. Once RTL is generated along with the test bench, co-verification is executed using the System C test bench to validate the design end-to-end against the reference model. At the same time, the simulation gathers performance statistics, tracking data movement through the interfaces to measure effective I/O throughput. This allows us to confirm not just functional correctness, but that the implementation meets the throughput and bandwidth targets defined in the specification.
Okay, thanks, Mike. That was a fantastic demonstration. We've now reached the end of the webinar, and so I want to thank you all for coming, and we will open it up for questions.
Hey folks, Charlie here in the background. I see we've got a couple of questions in our chat. One of them to the lovely folks at CircuitSutra. Do you support the CVX IF?
Hello. Can you guys hear me?
Yes.
Yep. So I think we have already got that answered. So since we are working on a higher abstraction level using simulators, adding a custom extension support is not as difficult as it would be in doing in RTL. So that's why we don't need that interface. And yeah, so that's the answer. Thank you.
I can add a little bit more color to that from a hardware perspective. The OpenHW Foundation has three processor cores that support the Core 5 extension interface, Core 5 XIF. It's the CV32E40X, which is based on the CV32E40P, but is a slightly different core. The CV32E20X and the CV32 and CV64A60X. None of those cores that I just listed are integrated into the Core 5 MCU. They could be. The Core 5 MCU is deliberately designed such that you can swap out the CV32E40P, swap in a different core. Doesn't have to be an OpenHW core, although it would be great if it was, but it doesn't have to be. And you could choose to use a core that had the Core 5 extension interface and go from there. So so currently the Core 5 MCU does not support it. There's no technical reason why it could not.
I can go ahead and answer the question about the LLMs.
Yep.
So the question is, which LM models did you use? Did you train some of them yourself? If yes, do you use only public available information? So we do not do any training, and we're pretty much set up to use any LLM, although so far I think we've been finding, that Claude does the best job. But whether it's Claude or some of the more modern codecs, LLMs from ChatGPT, the real key is that we use a skills-based system. So we have created numerous skills where we're essentially teaching how to do high-level hardware design. And that includes creating very concise canonical examples that describe the ins and outs of coding for HLS. And one of the reasons why this works so well is that coding for HLS, you're still using high-level languages like C++ and System C. And so the frontier LLMs that are out there and available already understand how to code for those languages. RTL is more challenging because there's not as wide of an available code base out there, but this is something that's coming eventually.
Hello, everyone. Thank you so much for this amazing presentation, all of you. And yes, we are excited to invite you all to our OCX experience. It's our flagship event for the Eclipse Foundation. taking place from April 21st to 23rd in Brussels. So with no further delay, I will share my screen. I already download all the live attendees and I put it in a software which randomly choose oh, sorry, Charlie, I need you to stop sharing to be able to.
I can
Thank
do
you.
that. Stop sharing. There we go. All sorted.
Perfect. Thank you so much. So we already upload all the people here. These are the first names. So I will. Good luck, everyone. And I will share with you. Okay, Truville, are you there in the audience? You are the winner of the OCX free ticket.